Hello everybody. I'm Chamal Srikumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. I, along with Ms. Rinju Mariam Roli, will be handling the course EC 303 Applied Electromagnetic Theory. In this lecture, we'll have a short introduction to the subject Applied Electromagnetic Theory. And this course is for the S5 EC students under the ATU syllabus. So, why should we learn the subject applied electromagnetic theory? We have all heard about the electromagnetic spectrum. So, electromagnetic spectrum is a range of frequencies that share some common properties and its used for particular applications. And this is called as the electromagnetic spectrum. The electromagnetic spectrum has a wide range of applications ranging from power transmission lines, antennas, radio frequency communication, microwave engineering, electrical machines, satellite communication, etc. So, since it is having a wide range of applications, it makes us enabled to learn the subject applied electromagnetic theory. That is, we should apply electromagnetic theory to particular applications. And you also know that light is an electromagnetic wave. And also any electromagnetic wave will travel with the speed of light if the medium is free space or vacuum. These are the information which we already know. And so it enables us to learn the subject electromagnetic theory. As you can see in this figure, it shows a mobile TV satellite where we have got towers and it is communicating to a satellite. The waves which are emitted from the towers are called as the electromagnetic waves, and the waves which are transmitted from the satellite are also electromagnetic waves. So, since it is a wireless environment, the electromagnetic wave travels through free space or vacuum from the satellite to the tower or from the satellite to the phone, etc. So, it has got a wide range of applications in the communication field. So, what is EMT? So, the basics of electromagnetics starts from the charged particles. So, these charged particles can be either in rest or in motion. So, electromagnetic is the study of charges which are either in rest or in motion. In EMT, E stands for electro or electric field. So, now we can see how an electric field is generated. So, any particle in nature is made up of atoms. An atom, when you consider a neutral atom, it will have equal number of holes and electrons. If an atom loses an electron, it will form a positive charge or a cation, and if it gains an electron, it will form a negative charge or anion. So when you consider a charge at rest, it can be either positive or negative. Now, when you consider ebonite which is made up of negative charges, and bring another ebonite which is also negative to near it, then it will repel each other. But if we bring a glass rod which contains positive charge near an ebonite rod, it will attract each other. So you can tell that like charges repel and unlike charges attract each other. If two charges are separated by certain distance in free space or vacuum, then there exists a force of attraction or repulsion between the two charges. And this force is determined by what is called as the Coulomb's law. According to Coulomb's law, the force is directly proportional to the product of the charges and it is inversely proportional to the square of the distance between them, and proportionality constant as a value 1 by 4 pi epsilon. And the direction of force is along the line joining the charges Q1 and Q2. So this represents the direction of force. It will be away from the charge if the force is repulsive, and it will be towards the charge Q1 if the force is attractive. Now, if this charge Q2 is made a unit positive test charge, that is Q2 is made as 1 coulomb, then the force value of the force is called as the electric field intensity. That is Q2 is made as 1 coulomb. So the force is 1 by 4 pi epsilon Q1 by R square AR cap. So the force experienced by a unit positive charge which is placed at a certain distance is called as the electric field intensity. So this electric field intensity is also a vector quantity. It is the same direction as that of the force. So from this expression, we can also write E as F by Q2. That's if you divide the force by Q2, we'll get the same expression as electric field intensity. So when you consider a particular charge, there is something which is around the charge which is called as the electric field intensity. That is the force experienced by a positive charge which is placed at a certain distance. So if you consider any charge, there will be a field around it. So we can see what will be the field distribution around a positive and a negative charge. So if you consider a positive charge, the field lines will be directed away from the positive charge. It is because if we place a plus 1 coulomb charge in this space, that is a positive charge, you already know that like charges repel each other. So since it is a positive 1 coulomb charge, they are both positive, so it will be a repulsive force. So the electric field lines will be directed away from the positive charge. Now, if you consider a negative charge and place a 1 coulomb test charge in free space, it is positive and it is negative. So the force will be attractive in nature. That is, it will be attracted towards the negative charge. So the field lines will be directed towards the negative charge. Now I am considering a pair of positive and negative charge which is made to separate at a certain distance. There exists an attractive force since they are unlike charges, but if we are forced to separate them at a certain distance, then there will be field lines which will start from the positive charge and it will end at the negative charge. And you can also observe that these electric field lines will not form a closed path. That is, if it starts at a positive charge, it will end at the negative charge. So we can conclude that the electric field lines are something which is formed around a stationary charge and it will be either towards or away from the charge depending upon the polarity. So now we have considered how an electric field is formed around a charged particle. Now we have seen how an electric field is generated. Now in EMT, next is M, it stands for magnetic. Now these charged particles are made to move with a constant speed through a conductor. So if the charges are made to move, that is the rate of change of charge is called as current. So due to the movement of the charged particles, there will be a current generated. Due to the current carrying conductor, we can have a magnetic field around the current carrying conductor. So the reason for magnetic field is current and it is formed by the movement of charges through a conductor. So you already know if you consider a bar magnet, there are magnetic field lines around it. These magnetic field lines, it will originate from the North Pole and it will end at the South Pole. But these magnetic field lines will always form the closed path. That is the observation which we can make between the electric field lines and magnetic field lines. This is similar to a positive charge and negative charge, but the only difference is that these magnetic field lines will be always forming a closed path. Now, if you consider a current carrying conductor, it is carrying current in the upward direction. Then according to the right hand thumb rule, we can find the direction of magnetic field which is around the conductor in the anti-clockwise direction. So this is how we can say that the current carrying conductor has a magnetic field around it. And you can also see in this figure we are having a battery which is connected to a conductor and the positive of the battery is connected to this end and negative of the battery is connected to this end. So the current will always flow from the positive of the battery to the negative of battery. Due to the current flow from the positive to the negative of the battery, we are having a magnetic field around the conductor. And now when you consider the direction of electron flow, it will be flowing from negative to positive because the current always flow in the direction of positive charge. So the electron flow will be in the opposite direction. It will be from the negative to positive. So due to these movement of electrons, there will be a current through the conductor, which in turn produces a magnetic field around the conductor. So now we have seen how an electric field and a magnetic field is formed. So electric field is formed around stable and stationary charge, and magnetic field is formed around a moving charge. That is, due to current we can form a magnetic field. So now we can take the electric field and magnetic field together, that is the electromagnetic wave. So these electrons which are moving with a constant speed are provided more energy, and it's made to accelerate or decelerate the charge. It's either we are increasing the velocity or decreasing the velocity. So due to this acceleration or deceleration of the charge, we will get what is called as the electromagnetic wave, and this will have a combination of electric field as well as magnetic field. So if you consider a current carrying conductor, the current carrying conductor will have a magnetic field around it according to the right hand thumb rule. That is, we are having a current and we'll have a magnetic field around the conductor. So due to this current carrying conductor, you know that current flows from positive to negative charge. So due to this current, the positive charges inside the conductor will be pushed up and the negative charges will be pushed down. So the electric field will be directed from the positive to negative charge. So if you consider any current carrying conductor, we'll have a magnetic field as well as an electric field. So this electric and magnetic field together forms what is called as the electromagnetic wave. And the observation which we can make is that this electric and magnetic field will always be mutually perpendicular to one another, and this will be perpendicular to the direction of wave propagation. So in this case, the wave is propagating in this direction. That is, we can see here C. That is, the electromagnetic wave is propagating with the speed of light in this direction. And the electric and magnetic field will be perpendicular to the direction of propagation. So this is what is called as the electromagnetic wave. This shows the animation of how an electromagnetic wave propagates. Here, the electric field is directed along the Z direction, that is a red line shows the electric field. Magnetic field is directed along the X direction and the wave is propagating in the Y direction. So you can see that the wave is propagating in Y and we don't have any electric field or magnetic field along the Y direction. So the electric field and magnetic field are perpendicular to direction of propagation, as well as the electric and magnetic field are mutually perpendicular to one another. So these are the properties of an electromagnetic wave. In this subject, applied electromagnetic theory, we require a prerequisite which is the vector calculus. That is, any charge, position, force, etc. all are vectors. So we need to study about the vectors before we go into the subject applied electromagnetic theory. In the first module, we will be covering the topics electrostatics and magnetostatics, which is the concept related to stationary electric field and magnetic field. So, in that, both electrostatics and magnetostatics, the concepts and theory related to this is dealt in the first module. In the second module and third module, we will be covering the electromagnetic waves, the theory, etc., the power, energy, etc. of the electromagnetic waves are covered in second and third module. That is, we'll have both electric field and magnetic field acting together. In electrostatics and magnetostatics, that is, with respect to time, there is no variation in electric or magnetic field. That is why it is called as electrostatics and magnetostatics. Now we have once we have covered the concepts related to electromagnetic waves, we will have to study certain applications of electromagnetic waves, and it is mainly in the two fields. One is on transmission line and one is in waveguides. So module 4 and 5 relates to the transmission line, and in module 6 we'll have the waveguides. So these transmission lines and waveguides are some guided media for the transmission of electromagnetic waves. That is, we can transmit the electromagnetic waves over free space, but if we require guided transmission, that is, we require a guided medium for the transmission, then we'll go for transmission lines and waveguides. So this is the flow of study for the subject applied electromagnetic theory. So in the subject electromagnetic theory, we'll be discussing what's called as the Maxwell's equation. There are separate Maxwell's equation for static fields and the time varying fields. So in the first module, we'll be dealing with electrostatics, magnetostatics, where we'll be having static fields. That is, we'll have the electric field and magnetic field whose rate of change with respect to time is equal to 0. And later we'll be dealing with electromagnetic waves where we are having both electric field and magnetic field coupled together. So Maxwell's equation forms the base for electromagnetic theory. So you have learned about certain concepts like permittivity, permeability, velocity of light in free space, etc. So we'll just see what are them and their values. So permittivity means that how the medium will affect the electric field. That is determined by what is called as the permittivity. That is, it is the ability of a material to transmit an electric field through it. And it is having a constant value of 8.854 into 10 raised to minus 12 farad per meter, and it is denoted by epsilon naught. That is called as the permittivity of free space. Now, permeability is something which is related to the magnetization of the material, and it will describe the ease with which the magnetic flux or magnetic field is formed within a component. And the permeability of free space is a constant denoted by mu naught, and it has the value 4 pi into 10 raised to minus 7 Henry per meter. The next constant is velocity of light in free space, and it is denoted by the letter C. And you already know that any electromagnetic wave will travel with the speed of light in free space. And it is given IC, which has the value 3 into 10 raised to 8 meter per second. This value of 3 into 10 raised to 8 meter per second is obtained using the equation 1 by root of mu naught epsilon naught. If we substitute the values of mu naught and epsilon naught, we'll get the value of 3 into 10 raised to 8 meter per second. Now, this is the case if the medium is free space or vacuum. Now, if the wave is made to pass through any other medium, then the velocity is given by the expression v equal to 1 by root of mu epsilon, where mu equal to mu naught mu r and epsilon equal to epsilon naught epsilon r. Here mu r and epsilon r gives us the relative permeability and permittivity of the medium. That is, if the medium is changed, it will have a value of relative permeability and permittivity with respect to the permittivity and permeability of free space. So we will have new values of mu and epsilon, and it helps us in finding the velocity of wave in any medium. These are the three main reference textbooks used for the subject applied electromagnetic theory. One is the Principle of Electromagnetics by Sadiko, Engineering Electromagnetics by Haidt, and Electromagnetic Waves and Radiating Systems by Jordan and Bum. So with this, I am concluding my introduction to electromagnetic theory. Thank you.